Thank you very much. So I'll be talking about, do we have the slides? Building machines that learn and think like people. And I mean, again, probably ground that's already been covered. I think the basic foundation for a meeting like this is that we've achieved great advances in AI, but the way I like to think of what we have so far are basically AI technologies, but no real AI. Nothing like a machine system that has the kind of flexible general purpose intelligence that humans have. And the question is, what else do we need? Or that's one basic question that we try to address in our research. We can also talk about whether we want to do that or what the implications of that will be, but this is part of laying the groundwork for that discussion. And again, I think maybe this echoes some things that Jan already talked about. A lot of the, and Alex also, a lot of the success, I mean, the success so far in particularly, engineering and industry and AI technologies has been driven by successes in pattern recognition technologies. That means very data-driven techniques with big data. The data is a big part of it. And techniques like deep learning and neural networks that use that data in scalable ways to recognize patterns in data. Okay. But intelligence is more than just pattern recognition. It's about modeling the world. It's about explaining and understanding what we see. It's about imagining things we could see but haven't yet. Solving problems and planning actions to make these things real, and then building new models as we learn more about the world. So the work that we've been doing, and I think many people see this as the next frontier, is to try to understand how this could possibly work. How can we come to machine systems that can model the world as flexibly and as richly, as deeply as humans do? My view, maybe much like Alex's, is that I think we're decades away from AI systems that can do this as powerfully as humans do, and with a technology that's mature enough to deploy in applications at places like Google and Facebook. But right now, more on the academic side, we're starting to understand some of the fundamental principles and computations, mathematics behind this. People often like to talk about an AI to make analogies with the history of the physical sciences. If our goal is to get to the moon, to have some kind of a moonshot, as Demis likes to talk about, where are we in the history of our science? And I always like to say, I think we're kind of at the stage of Galileo right now in terms of the idea of, where just starting to understand how to put math on the really deep ideas. And I guess if we're at the stage of Galileo, then the Pontifical Academy should start to be interested. So I'm glad to be here talking about it. What I will talk about here are two particular case studies that we've been doing in our group recently, trying to just show some of the very first steps about how we can capture these more human-like model building abilities. One has to do with one-shot learning. How, in contrast to the data-hungry approaches in AI right now in the industry world, how can humans learn such rich concepts from so little experience, often just a single example? Or problems of common sense, again, things I think people have been already talking about. How can we, when we look at an image, say, see a whole world of physical objects, their interactions, and our own possibilities to act and interact with them and with other people, and not simply classify patterns in pixels? The approach that we'll talk about is very related to what Alex was talking about, and I think maybe partly what Jan was talking about. We call it probabilistic programs, and we also talk about program induction as a learning method. And I'll try to give you a taste of this for those of you who haven't seen this, but in some sense it's an old idea. One of the earliest scientific theories of perception is Helmholtz's idea. It's sometimes called analysis by synthesis, or the idea that, say, the visual system is trying to invert, to effectively have a causal model of the processes in the world that generate scenes, the stuff out there in the world, and then images, the light coming into our eye from those scenes, and then to invert that, to work backwards from the observed patterns of light to the stuff out there in the world that causes it. In a sense, it's not just about perception. In a sense, it's the original theory of cognition. So Ulrich Neisser's book, Cognitive Psychology, in 1967, 100 years after Helmholtz, the book that gave the name to the field of cognitive psychology, basically argued for the same view as a unifying theoretical paradigm to think about language, vision, action in terms of these hierarchies of structured representations of the actual causal processes in the world that the mind has to manipulate. What's new now is that in the last few years we have computational formal models to make these ideas real, not just to draw pictures or to put words on them, and to solve them in compelling problems. So we call these probabilistic programs, and it's the idea of doing a kind of probabilistic inference, in particular a kind of Bayesian inference, although often a very approximate, few sample-based Bayesian inference, over symbolic representations of the world. And this is, I think, the key difference between a lot of more, say, probabilistic approaches in neural networks is that it's probabilities over symbols rather than over numbers. There are numbers in there too, but the really interesting new thing is how to combine probabilities and symbols. Another way to think of this is it's the probabilistic brain, like Alex was talking about, meeting the symbolic mind, which is, again, probably the oldest way to think about intelligence formally, is as something like a symbol system, logic, and so on. And it's been a great challenge to understand how can these two kinds of mathematics, the mathematics of probability and the mathematics of logic and other kinds of symbol manipulation and symbolic expression, how do these meet up? So we and others have been making some progress in doing this, and I can't really go into the math here, but I can show you the kind of things we can do with it. So first in one-shot learning, and here I'll say this is work that was mostly done by Brendan Lake, a former PhD student of mine, and now a postdoc at NYU at the Center for Data Science, where Jan is also in charge. So to set up the kind of problem, it's very broadly motivated by how any child learns basically the meaning of any word. It's all about often just one instance. Like the first, you might if you were a young kid, you might learn the word horse from seeing one horse out in the country. If you forgot what that's like, though, imagine the first time you saw one of these segways, you'd have relatively little difficulty identifying, say, other instances of that category from other, say, similar but different kinds of transportation systems. Or to show you something that maybe is a little bit more novel, most of you probably don't know what this object on the top is. It's called a cam, unless you're a rock climber. It's a specialized piece of rock climbing equipment. But you would have no difficulty recognizing, even though you've only seen one labeled example, down on the bottom, some other cams, these ones here, even though they're different in basically every way. They're actually different shapes, different colors, and different positions, and so on. So how are you able to do that? Well, Brendan, and also working with Russ Salakhutdinov and I, tried to tackle this in a domain that was simpler. This is where, again, we see the difference maybe between the sort of industry technology setting and the academic setting, although we're very much inspired by work that Jan and colleagues did back at AT&T Labs a couple of decades ago, where they built a big real-world data set for the time of handwritten digits. They built a data set of thousands of examples of the digits 0 through 9 as a test bed for developing a whole range of pattern recognition and fairly sophisticated pattern recognition ideas. We think solving this one-shot learning problem with, say, real-world objects like these, the cam, the segways or the bicycles, is still too hard. Despite advances in machine vision, we don't have AI systems that see these objects and images as richly as people do. But these handwritten characters are a place where we can work out some of the basic ideas. So we built a data set that, unlike the MNIST data set, which has thousands of examples of a couple of categories, or 10 categories, here we have a few examples of thousands of categories. It's called omniglot, and it was inspired by a website that catalogs all of the world's writing systems. You can see many instances here of one instance of each of a different character. And within this big data set, there are many of the world's alphabets. There are also many made-up alphabets, because it's another interesting property of even the simple domain of simple visual concepts, that you can make up new concepts, and we can recognize the alphabetness of each of these systems, as well as each of these individual symbols as distinct from the others. We can do this kind of one-shot learning here. So for example, if you look over on the right, if I can get my cursor here, here's one example of a character in an alphabet you don't know, but if you look closely at all the other examples over here, you can probably see one other one. Everybody see where it is? Just clap your hands when I get to it. Yes, that was a very gentle clap, but you got it. Yeah. Okay, so again, how are you able to do that? Well, the model that Brendan and Russ and I introduced here, we call Bayesian program learning, or that's really an approach, and we have one specific model in this domain, and I don't really have time to tell you the details, but the basic idea is to represent each of these concepts as a kind of a program. In this case, it's a program that generates the concept like a high-level action program. And you can get the basic idea, though, by looking at this new character and imagine how you would draw this character. So just draw it in the air. And you probably did something like this. This is what 6 participants in our studies did, right? So our model tries to capture how you're able to do that. And it does this by using some general principles of it's got a causal model, and it's got a compositionality. And this idea that this is, I think, the most important feature of a programming language in computer science that we want to capture in the representations of knowledge in our probabilistic models, is that they have pieces that compose together into larger units. And that's the way to build up models of increasingly complex structure in the world. In this case, there are two levels of programs. There's one level here and a higher level. And the only thing you have to think about is that the low level programs capture each individual character is one of these programs, and it's probabilistic to capture the variability. So every time you run this program, you get a slightly different version of the character out, and that's what captures the variability in the concept. That will allow you to classify new things by saying what's the most likely program that would have generated them. Learning, though, means figuring out that program, inducing or constructing that program. And here again, as Alex mentioned, the prior is central. The prior comes from another program. This is a program generating program whose output is one of these low-level programs. So the prior is also captured by a program that generates possible programs, and that's how we imagine new characters. And then by doing probabilistic inference in this model, we're able to capture this ability to learn a new concept as one of these low-level programs from maybe even just one instance. So this model is able to capture what's really quite high levels of human performance. I won't go through the details of this data graph, but basically this is the error rate of humans. That's the pink bar over there on the lower left. And humans are almost perfect. They're under 5% error rate, as is this Bayesian program learning model. But both simpler versions of this structured Bayesian approach or even state-of-the-art deep neural networks can be pretty good, but they're still 2 or 3 times worse than people. Maybe a more interesting demonstration is this here, where we can ask people, just like our model, to imagine new instances of a character. So here, for example, these are the ones generated by the machine, and you probably would have a difficulty. In fact, I can tell you, it'd be very difficult for most of you to tell those apart from the humans. Try here. Can you see which ones were the machine and which ones were the humans? Can anyone tell? It's very difficult. Here's the machine. Again, can you tell? No. Okay. So hopefully you can see the idea there. We worked out this model in just the one particular domain of handwritten characters, but we've been applying this in a number of other settings, other kinds of cultural symbol systems like learning spoken words from one instance or gestures, more interesting kinds of visual objects, and inspired by some of the great successes from Demis's group at DeepMind and others in the deep reinforcement learning world, looking at how people learn complex novel skills like video games, where again, at the moment, people can learn much, much more quickly than our best AI systems, and we think similar ideas can help there. The other application area I want to just briefly mention is what we call common sense scene understanding, where we look at, for example, we look at scenes like these here, and we don't just recognize the objects, but we get a sense of the intuitive physics and the intuitive psychology. So we see in, say, the crowded workshop scene up here in the upper left, we see that the table is supporting these objects. If the table were bumped, which ones might move or fall? If the table were knocked over, what would be disturbed in the scene? What's attached to the back wall, or what could you lift off? The scene down here in the lower left, you see all these pieces of wood, you see a house being framed. You don't see any nails, but you know where they have to be so that the thing doesn't fall over. At least approximately, you could make good guesses. You could see that the stack of dishes at my local cafe, where Cedric has been and had coffee with me, would have to be restacked before you go and bust those dishes. Or in these scenes over here, you don't just see the people, but you get some sense of what they're thinking, what they're looking for in other people, what their goals are. The street scene is particularly compelling, and also from an AI technology point of view, where self-driving cars are, I think, one of the most exciting and also potentially impactful, positively and negatively, AI technology. This ability to get the kind of common sense understanding of other people and their goals is one of the key things that's been missing from self-driving cars. So here's a couple of quotes from news articles when Google's self-driving car first went public. This was back in 2012, and they pointed out that the key thing they're missing is the ability to capture the intuitions that human drivers have about, say, what pedestrians or other drivers will do. Okay, though there's been a huge amount of economic investment and smart people developing technology in self-driving cars, this is still the main problem, right? If you look at the news articles that have been written in the last year, this is exactly this, they still talk about this challenge. So I think it shows the persistence of this challenge shows how deeply important it is and how it's not something that is going to happen in the next few years, I think, to really have this kind of general purpose, say, social understanding in machines. You can see all of this behavior in very young kids, and I think we'll hear more about that from Laura Schultz and Liz Spelke and others tomorrow. But just how kids play with blocks or play with each other, or in this wonderful video from Felix Warneken, which studies the spontaneous helping behavior of 18-month-olds. Look at this 18-month-old here who's watching Felix there, just kind of, I don't know, doing something. He gets a sense that, right, maybe he's trying to open the door. And then the 18-month-old goes over here, opens the door, looks inside, because wonder what's in there, steps back, and here's the best part right now, looks up at Felix, and then tracks his gaze to see. So, I mean, and their studies are full of this kind of behavior. This is not just a one-off case. If we could understand what's going on inside that kid's head, his ability to analyze the physics of the situation, the actions that Felix is trying to take subject to those physical constraints, and then to see if he's interpreted the right intention of Felix so that then he appropriately helps him achieve that intention, and then tracks Felix's action to see if he's right. I think that's a grand challenge for AI right there. So we've been working towards this kind of idea, again, with small steps, based on now probabilistic programs over what we call game engine representations. Now, here the programs come from a different area of technology. The video game industry has developed wonderful ways of simulating complex three-dimensional worlds that a human player can explore from a first-person perspective. Often it involves shooting things and people, but we won't go into that here. And the tools, the graphics engines, the physical simulation engines, and the AI planning engines, the simple engines that let this world be inhabited by other agents who have very simple kinds of goals and ways of implementing those goals. By doing probabilistic inference over those representations, we can capture some of these basic aspects of common sense. So for example, in intuitive physics, this is work that was done by Battaglia in our group a few years ago, who's now also at DeepMind with Demis, and also with Jess Hamrick, who's a PhD student and also has a DeepMind connection. We ask people, for example, to judge how likely any one of these stacks of blocks is to fall over. And then we can model that by basically just a perceptual system which approximately reproduces the stack of blocks in a physical simulation, and then just runs a few time steps forward to see what would happen. And that provides a pretty good quantitative model of people's judgment. So here this plot just shows each dot is one of 60 different towers of blocks. On the vertical axis is the average judgment of humans, how likely this is to fall, and just making a couple of these probabilistic guesses, like a few likely future outcomes, and then averaging what happens across those. That's what's shown in the x-axis, does a pretty good job of accounting for people's behavior. Or just to illustrate this maybe a little bit in a less familiar task, because this is a task which could be amenable to pattern recognition, like Jan, I think, did you talk about some of the excellent researchers at Facebook with Jan have been building neural nets to capture this sort of task, but our intuitive physics is much more flexible. We can take tasks that you've never actually done before unless you've seen this talk. So for example, this one. Suppose this table is bumped hard enough to knock some of the blocks onto the floor. So you tell me, is it more likely to be red or yellow? Tell me, red or yellow? Red. Okay, good. How about here? 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 You're just here? 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 Okay, so you can see some are very obvious, some there's more uncertainty. That reaction time latency, again, echoing some themes that Alex talked about. If it takes you a little bit longer, sometimes that's a good sign of uncertainty. But ask, how are you able to do this? I could just keep going on all day, although I'll stop soon. I only have a couple of minutes left. For me, really the best way I can think about this is the way our model does, and I'll just show you here. This is an illustration of running one of these simple physical simulations in this game engine. It's not totally realistic, but what you can see is here the table is bumped with a small bump, here it's bumped with a large bump, and different things happen, but basically the same thing happens at the grain we can think about and describe, which is all of the yellow blocks go over and few of the red blocks. You only have to run the simulation for a few time steps. That's enough, just a few time steps to get that answer. So we think this is an algorithmically and also cognitively plausible mechanism. And here you can see that model for this much weirder task giving an equally good account of people's judgments. And for many, many different tasks, including which way will the blocks fall, what happens if the blocks are made of different materials and have different masses, what happens if they're different shapes and sizes, and so on. And this is the kind of thing that to date has been hard, or neural networks that are just trying to do pattern recognition without building these kinds of richer probabilistic and symbolic models of a world of objects and their interactions have had difficulty scaling to. Just the very last thing I want to show you is a little bit about the intuitive psychology engine, the other side of the picture here, where physics is also part of this, but now we have programs that also capture the planning process. So how an agent might choose actions, which again, in some kind of approximately optimal way, whether or not humans are optimal, as Alex and Stan were talking about in certain decision-making settings, we think that our intuitive theories of human action have optimization at the heart of it. And again, maybe we'll hear about some of this from the developmental psychologists tomorrow, but there's research both in young infants and in slightly older children, some of which done in Laura's lab by Julian Hara-Edinger, and some of which is currently going on in Liz Spelke's lab by Sherry Liu and others, showing that, again, from very early ages, young people understand other agents' actions as something like an approximately efficient way to achieve your desires given your beliefs, which we can formalize as something like a kind of expected utility maximizing planning. And those beliefs are also formed, of course, by the agent's percept. So we can't, just like we can't yet build our program induction models on segways, we can't yet apply these models to those scenes over on the left, but we can apply them to much simpler scenes like this food trucks domain here. So for example, here I'll just tell you the story for a second. There's an agent, let's say a hungry graduate student at one of our universities, who wants to go looking for lunch. And on his campus, there are 2 parking spots, the yellow spots here, and there's 3 different food trucks that come to campus each day. There could be a Korean truck, a Lebanese truck, or a Mexican truck. But of course, on any one day, only 2 of them can find a spot. So let's say he does this. He comes out of his building here, and he can see things in his line of sight. So he can see that there's a Korean truck here, but he can't see what's on the other side of the building. So he goes here, he goes past the Korean truck, he goes around to the other side. Now he can see that there's the Lebanese truck there, and as opposed to the Mexican truck, and he turns around and goes back here to the Korean truck. So the question for you is, which is his favorite truck? What do you say? Well, maybe you can't tell. If you had to guess, which is it? Mexican, yeah.
Mexican, yeah.
So you might say K, or you might say Mexican. If you had to choose between K or L, you'd say K. But if you remember that there's also the possibility that the Mexican truck would have been here, then the best way intuitively that we explain his behavior is that he really was looking for Mexican. He thought it might be there, but then so he went to look for it. But when he saw it wasn't there, he went back. And that's what our people make those judgments, and our model is able to capture that. And again, it doesn't have to be trained on a big data set, and indeed, there isn't really any pattern directly in the data. It's not like he's moving towards the Mexican truck. It's just the Mexican truck isn't there. It's only in your mental representation of that agent's mental representation that you can understand what's going on here. These models can also quantitatively capture what people do. And what we're doing right now is we're trying to take these same models, one step towards what would be, I think, a real AI application, is to look at, say, how, for example, people reach for things in the real world, like this woman here, or here, imagine you're trying to figure out, like, which object is she reaching for, and how quickly can you figure out what she's reaching for? It depends on both what she's moving towards, but also her understanding of the physical constraints of the table. If you look at this guy over here, this is Tao Gao, you might wonder, why is he doing that funny reaching motion? But can you see why he's doing it? It might not be easy to see, but there's like a glass panel that he's trying to reach over, like a sneeze guard at the local deli or patisserie or something. Okay, so this is an efficient action. It's a weird way to reach for something, but it's an efficient way to reach if there's a physical constraint. Okay, and you can see here very, very clearly, I think, how our understanding of what somebody's goal is directly tied up with understanding the constraints and understanding their approximately optimal planning. So we can build models that kind of run these planning algorithms in reverse to try to take situations like, or take stimuli like this and infer online, this is the result of inference about all possible targets, what do we think her goal is? And you can see that around the time you start to be confident of what her goal is, these models do too. And they do it by basically running, in some, I think, very overly complicated way at the moment, a set of robotic simulations where they try to solve the planning problem for all the possible goals and figure out in a Bayesian sense which one best explains the data. And just the very last thing I'll show is that, again, where we're working towards is inspired by that 18-month-old helping Felix Wernicke there, is to understand how these can also work in a multi-agent setting, where to understand, okay, well, you see Tao here is trying to help Yibiao, where Tao seems to be getting Yibiao's goal and doing the best thing to help him, or over here, you see a less helpful interaction. All right, so what does it mean to help or to hinder, or to cooperate or to compete? We can take these agent models and combine them recursively, where we have one agent whose beliefs and desires depend on the beliefs and desires of another agent. So we think by by just continuing to push out these game engine models, but allowing agent models to be recursively embedded inside each other, and also each one also has as a world model the constraints of the physics there. This is a toolkit that will, I think, allow us to build some pretty interesting common sense systems for intuitive physics and intuitive psychology. So just to conclude, I've tried to argue, again, I think consistent with many people here, that intelligence is more than just pattern recognition, and AI has to be too. It has to fundamentally, there's many things it has to be beyond that, but one is building models of the world to support explaining, imagining, planning, and thinking. Our cognitive science points to fundamental principles of how the mind builds models, the need to combine probabilistic inference with symbolic representations, to use these symbolic representations to capture compositionally or modularly the causal processes in the world, to be able to really represent the physical objects and the intentional agents out there. And on the technical side, these new tools, probabilistic programs and program induction and the game engine in the head, are beginning, but just beginning, to let us do this. There's many things that I'll just put out there, my thoughts that I'd like to discuss with all of you. You know, how can we, and on what timeline could these ideas scale up to a mature platform for engineering AI technologies, like in the setting that would interest Google, Facebook, Uber, Amazon, or other whatever new companies will arise in the next decades. How might these approaches integrate with other AI successes, such as deep learning and neural networks? And then a number of, I think, really interesting philosophical connections that some of the speakers like Stan and Laurie Paul might talk about tomorrow. Links to questions of consciousness and the self, issues of morality, like what are our intuitive moral concepts, and how might they be defined on top of some of these common sense intuitive psychology representations. And even, I would venture, a version of the mind-body problem, but I'll just put that out there as a teaser. Thank you.